Good morning, my beautiful 1030 class. I hope your day is going great. We are learning 9A, section 9A in this video. It is on functions, and functions are awesome. They are the building blocks of mathematical models. We use modeling all the time. You might have heard of modeling lately with the coronavirus and the models that they have. You've seen curves and functions that show how many people will obtain the disease or get the disease, how many people will actually recover from it, how many people will die from it. Those are all done with information or data that are given to the researchers, and they get that data and they create these models. They're all based on the facts they've been given, and then they predict the future using the data that they have. It may not be impossible to predict the future precisely, but we needn't go forward blindly, right? Things change. In fact, we have this quote here from 500 BC, nothing endures but change. And we know that more than anything, don't we? That the only thing that always is there is change. Things are going to change. But if we learn the basic principles used in modeling, then we can mathematically model our world and then use those identifying relationships that describe how one variable changes with respect to the other to help us go forward in the best possible way. So these relationships can be described, sometimes they're described with equations or in words, sometimes you are given a graph, and we'll talk about those in our lesson today. So the first thing we need to understand is functions have a couple of parts, and you see them there. They have an independent variable, which is generally the x, and then a dependent variable, which is generally the y. Usually we see this in an ordered pair such as x, y. But because our world has so many different things that are modeled, then all of a sudden we just need to claim them. Instead of saying x, we might have an L, or we might have an H, or we might have a T. We just say independent variable. And again, a variable is just a letter that represents a number. And then dependent variable is second. So first is independent, second is dependent, x is generally first, y is generally the dependent variable. So a function describes how a dependent variable changes with respect to one or more independent variables. When there are only two variables, they're often summarized as an ordered pair with the independent variable first. So that's what you see right here. All right. The dependent variable is a function of the independent variable. If x is the independent variable and y is the dependent variable, write the function. We're not going to actually write the function right now in terms of y equals f of x. Instead, we're going to just look at what the function is as a model and which is independent first and which variable is dependent second. Now, for me, it's easier to figure out which one is the dependent variable first. All right? For instance, I'm just going to pull a function out of the air that we use sometimes. If you take a shower, when you take a shower, you get into the shower and you turn on the water. Every minute that shower is on, you use up 8 gallons of water. So that would be a function. You would do the gallons of water is equal to 8 times x, and x, or we'll do m, 8m, so g equals 8m. M is the minutes that you were in the shower, and G is the gallons of water used while in the shower. So I always say to myself, which one depends on the other? Do the gallons of water used depend on the minutes that you're in the shower, or do the minutes that you're in the shower depend on the gallons of water that you use? And of course, it was the first option. The gallons of water used when you're in the shower depends on how many minutes you're in the shower. So water depends on minutes. Water is the gallons of water is the dependent variable, dependent on the time, the minutes in the shower, and the minutes would be the independent variable. And that's a lot easier for me to figure out first. First dependent, and then independent, and then I can figure it out. So we're going to try it. We have a few examples here. It says identify the dependent and independent variables and then briefly describe the expected relationship. All right, so the total distance a car has traveled after various amounts of time. I'm going to go to my paper so I can write it down. So the total distance a car has traveled after various amounts of time during a road trip. So this, I don't know the best way. I'm going to show you what I do. I think, okay, those are my two variables. I say distance is a variable, time is a variable. So I've got my two variables. And then I say, does distance depend on time, or does time depend on distance? And of course, distance depends on time. The distance the car travels depends on how much time you're traveling. So distance is going to be the dependent, and time is going to be the independent variable. We always list the independent first, so time goes first, and then distance second. The other things you can think about here, time, as time's increasing, your distance is increasing, and you're probably going to have quite just a linear line there. All right, next one. The way the price of a new smartphone affects the number of people who buy it. So once again, price, number of people who buy it. This is a little different because we have two things going on here. If a price is really small, then not very many people are going to buy the phone. They're going to think it's cheap and it will break quickly, and they might not want to waste their money. If the price is really expensive, people don't have that much money and they say, I'm not going to buy that. So we have, excuse me, two times when people aren't going to buy the phone. But if the price is right in the center there somewhere, then people are going to buy it. But whatever the case, the number of people who purchase the phone depends on what price the phone is, right? So the number of people buying it depends on the price. The price doesn't depend on the number of people buying it. The number of people buying it depends on the price. So number of people buying it, I'm just going to call them buyers. Number of people buying it is the dependent variable, I said, and then I wrote it in the independent spot. So whatever the price is, it's independent. You can set the price at any price. And then the number of buyers depends on what that price is. This graph's going to look a little different. Not very many people, of course, we have the price here, along here, and then the buyers here. So first of all, if the price is not very big here, not very many people will buy it. And then as the price gets to that sweet spot right there, we have a max buyers. And then as the price continues to increase, gets too expensive, and then we have less buyers. So anyway, price and the number of buyers are the independent-dependent variable, just like that. All right, C, the list on your grocery store receipt giving prices of items you purchased. So we have the list and prices. Now, this is, I know what they meant here, and that's the problem. It's really hard to determine, well, what did they mean by that? What they mean is your total bill at the end is going to be dependent on how many are in your list, right? If you have if you buy 2 items, your price is generally not going to be as much as if you buy 25 items. And again, I don't really like this one because it depends on if you're buying a television, and that's the only thing, but you're comparing that one purchase of a very expensive television to the purchase of 5 different vegetables. Then you have 5 different vegetables listed. It's a longer list. So we're just talking about general. So just don't worry about that. Just think in a general level. The list and the price that you pay at the grocery store. Now, the price that you pay depends on how long or the amount of things that you purchase, right? And I guess this is a grocery store, so that will probably help with, we're not going to buy a television, a very expensive one television at the grocery store. We're going to be buying a bunch of different things. So the longer the list, the higher the price. So the price at the end depends on how long a list that you actually purchased. And so list, we'll call it length. I don't know. That's going to be first, and then your price is dependent on that list, so price is the dependent value. All right? That's how that goes. This one's going to be kind of the same as the first one. You're going to have list length. As it increases there, the price increases there, so it's going to look kind of like our first graph. All right, the effective income tax rates on government revenue. Now, tax rates. If I have higher tax rates, then the government's going to make more money, right? If I have lower tax rates, the government's not going to make as much money. So which one depends on the other? The revenue that you get, the government gets, is dependent on the tax rate they charge. So dependent, independent. So for this one, we're going to have our tax rate first and then revenue second, okay? And it's probably going to look like that. I'm going to draw it again, but it'll look like that. The higher the tax rate, it's probably going to increase. It might not increase in a linear fashion. It will probably be a curve. But whatever the case, it's tax rate, then revenue. For independent, then dependent. The way in which the population of endangered elephants depends on the number of park rangers enforcing anti-poaching laws. So here we have number of park rangers, and then we have population of endangered elephants. Now, do the number of park rangers depend on the population of endangered elephants, or does the population of endangered elephants depend on the number of park rangers? Well, I would say that that's the way it goes. The population depends on how many park rangers. The more park rangers you have out there enforcing the rules, the higher the population of endangered elephants will be. There won't be as many poachers out there. So we're going to, because of that, our independent value is number of park rangers. All right, and then we'll just do endangered elephant population is going to be our dependent variable. All right. Okay, so with that, let me go back to my video here. We'll go through one more slide before we move on. Oh, I guess we'll do this one. Okay, so many functions describe changes with respect to time. The weight of a child and the consumer price index both vary with respect to time. So those are things that vary with respect to time. The more time that goes by as a child, and we're not talking about adults here, we're talking about children, the weight of the child increases as they increase in age and they're growing up. And then the consumer price index, they're changing, the index is changing with respect to time. But not all functions involve time, even though a majority of them do. Not all of them do. For instance, a mortgage payment, that is a function of the interest rate. If you remember when we dealt with mortgage payments, and each payment, the mortgage amount didn't change that you paid, but the amount going toward interest and the amount going toward principal does change. And that depends on which payment it is. So the payment amount depends on the interest rate. And then similarly, the gas mileage of a car is a function of the car's speed. The higher, the faster the car goes, the less the gas mileage the car gets. So because the mileage is different at different speeds, we have a function there. So we have to kind of look, and we can assume a lot of times that we're going to have functions that have an independent variable of time, but sometimes we're not. So don't always just assume it's going to be time. So with that, I'm going to pause the video so I can upload it appropriately, and then we'll start again right there on this slide.